So in EAS663, I think because now you should be clear, you have 663, 661, 664, 662, 501, and then EAA, so many 666. So 663 has two parts. No? First is the dynamics. The second one is on stability. So dynamics, you already settled. Okay, so those are the things that you are expected to know that will be asked in the exam or in the test or the things. So 663 is mainly dealing with stability. And it is mainly dealing with how to, okay, sorry, can you hear me now? Sorry, just now I forgot to on the mic. Can you hear me now?
Yes, I can hear you. Yes, I can hear you.
Can you hear now? Okay. So now, if you're asked to use method of neutral equilibriums later, we'll see another 3 methods that you are going to use, plus this become 4 methods. Okay, so you have to know method of neutral equilibriums mean what is the things that you have to do. You have to assume the slightly bent configurations, and then you have to write down the governing differential equation and you solve them. So those are the things that we have gone through. And we have make use of this to look at a pin column. Okay, pin fix column, fix column, and fix free. So these are the 4 classical end conditions which is form the basis for us to understand the P critical of column. Okay. So all these things, if you go through again the notes, you see the steps, common steps that you have to go through, and you need to know how to solve the governing differential equations. Okay. We have also looked at elastically restrained. Yeah. So meaning that is not completely fixed, not completely free, not completely pinned, is connected to other members. So we have elastically restrained, meaning that the restraint here comes from other members, not necessarily as support. Okay. So those are the things that you have gone through. So pin, fix, free, and elastically restrained. If we look at one example where it is connected to other members. Okay, maybe here is one member. The only thing is the column is not like what we have here, but it is elastically restrained. And from there, we see the effect of restraint. Yeah? Restraint here, we means restraint here in terms of, do you allow this? So restraint here means we look at if this is 0 or not 0, which is, or the rotation is 0 or not 0. Okay? So those are the restraints that is important for us to know, because the higher the restraint, the P critical will be higher. The lower the restraint, the P critical will be lower. And we have also looked at the concept of equivalent or effective length. Okay? We have looked at the concept of effective length. Okay? So effective length is, you have to know what is the definition of effective length. Okay? Effective length is also one of the things that is important to know when we are dealing with member in compression. We use a simple LE. Sometimes in the book it is also used as other symbol. Okay, lambda. It can be used different symbol in different sources, but the most important thing to know what is the definition. Okay, is an equivalent length of an equivalent Euler column. Okay. So we have for pin, fix, and fix, three different equivalent effective length. And what is the good things about effective length is the P critical, you can put them in the form which is standard for all columns that we are interested in. Okay, so this can be applicable to all this kind of end condition as long as we know, as long as we can evaluate what is the effective length. So we get P critical. Okay. Then last week, we also look at the limitations of this Euler theory. This is based on Euler theory, which is for perfect column, and for very slender column. So this is applicable to perfect column and very slender column. And how do we look slender? We look at the slenderness ratio, okay, where R is equal to square root I over A. This is the radius of gyration. Yeah. Radius of gyrations in mm or in centimeter. So this is a very important thing of the section properties that has a big effect on the capability of the members to resist compression, to avoid buckling failure. So if this is only for very slender column, means for short column where the slenderness ratio is low, then this is not applicable, because for short column, the failure is because of material failure. So because of that, we look at one of the formula. This is Euler formula, but we go to another formula which we can be applied to both slender column and short column. Okay. So we look at that, and that is what we call the Rankine formula. So if you come across the terms Rankine formula, which is the starting point is 1 over P or 1 over PS plus 1 over P critical. This is for both short and long column, or slender for both. Okay, short and long columns, we can use this. Okay. And to use this, we have this formula, which is, I think it should be sigma S 1 plus K LE over R squared in LE over R. So this is the formula that we will we're looking at, okay, where K is a constant, which has to be determined experimentally. Okay? And if we make use of this, then if we know the sigma S, which is related to the material capacity, and if we know the N conditions, then we know the effective length. We can get the effective length. Then if we know the sections that we want to design, we can get the R. Then we can estimate what is the load which we allow on that column to avoid buckling failure. Okay. So those are so far the things that we have discussed, and this is this Rankine formula is for perfect column, but it is different from Euler formula. It is applicable to short and long column. Short and long. Okay. So that is somehow what we have gone through in the last 2 weeks, okay, in the last 4 hours, again, because in the last 2 weeks, 6 hours, we missed 2 hours. So this is what we have gone through. So I briefly revise with you again, okay, to bring out what today I want to discuss with you, okay. So now we want to go to the next stage of. Any questions on this? What we have? K, I think there is a value K here, which is K, there is a, it is a constant where it is relying on the materials that we use, okay? So for the value of K that I show on the whiteboard, it is, if we go to the Rankine formula, so K, I think K, we can get the K from, so K is equal to this sigma S over pi square E. So it is very much dependent on the material that you use. For timber, for steel, for concrete, for aluminum, we have to determine this experimentally. It has different range of the values, okay? So I also given you exercise that I given you exercise on use of Rankine formula, two questions that you can find on the e-learning as well. And to be familiar with how to make use of these equations, how to make use of these equations for getting the load which is allowed, that we allowed to apply on the column to avoid buckling. Yes. A is the same as K. I think in the exercise, I think the different symbol are being used. You mean the symbol? Yeah. The A here is actually the A here is actually the K.